Can you see it? Check if you can see it in Car's page. كما على قل ما نبحثها في سكان. لا كم هر يعني على قبل سي أو برويتو به خير. الآن یک نفر هی بسیت توانی یکم بخونید همش صوتها مريمانة ثانية. السلام عليكم. بخير بخير. سلام بخير. سلام خير. شو جانا توين دسبي؟ لا فينا. I would like to thank Dr. Bahman for organizing this whole organization and also this talk. As he tried to explain, I think it is very important for the Kurdish academics in UK and more generally around the world, because we don't really have any meaningful network for communication of all these people. There are many individuals, but they are all seem to be isolated. Or sometimes maybe there are organizations that are connected to political parties, and it's really not good because in many ways it overshadows the main objective of an academic network. And as Karl Bahman said, there are 54 organizations only in London for Kurdish people, but there are only 2 of them that deal with education and research and so on. And I think there are maybe 100 TV channels, Kurdish TV channels around the world, and none of them even talk about research or education or anything. So, unfortunately, there are political and cultural reasons for this. We are not very organized. We haven't learned to be organized and cooperate. Our culture, especially the political landscape, is not very promising because you see a lot of political parties, instead of cooperating, they are fighting with each other. And we just haven't learned to be cooperating and organizing something that helps everyone. Anyway, in this talk, I want to talk about mathematics in 21st century. Maybe it's better I should say that it's about mathematicians in 21st century, because I cannot really talk too much about mathematics because it needs a language, it needs background. Without this background, it's difficult to understand. But at least I can tell you what mathematicians do. What is the job of a mathematician? Is it just counting from 1 to 10,000, or there is something more to that? Of course, it depends on the place that the mathematician works. So this is more my own perspective, my own experience in my university, which is a research-focused university. So there are some other universities that are focused on teaching, for example, and then duties, responsibilities may be a little bit different. So in my case, there are many universities in UK. The research they are research focused, so this applies to them. And this is also not only about mathematics. It actually, maybe you have a similar situation for many other fields. So the most important duty, responsibility of a mathematician is doing research. And what research means, it basically means discovery. It means discovering something new that people did not know before. It means, in practice, it means that you choose a topic. There are many different topics in mathematics. Mathematics is a very huge, very vast field, and you need first to choose a topic. When you choose the topic, then you need to read articles, you need to read books, read the literature about this topic. You have to learn the topic first. Again, as I said, this is not just for mathematics. If you work in psychology, it's exactly the same thing. You have to choose something and then read about it, learn about it. And then, especially in mathematics, then you need to find important problems in this field, in this topic. Problems that people could not solve before. Something that if you solve, you are adding something new to the subject. And there are many types of problems. Some of them are important, more important, some of them are maybe less important. So it depends on the ability of the mathematician. If you think they are very very clever or whatever, you have a good background, then you go for a more difficult problem to solve. And these problems are not just about mathematics. Sometimes they are motivated by other problems outside mathematics, for example, physics, biology, or computer science, or engineering. There can be many different ways where these problems come into the topic, come into the subject. And then you have to solve the problem. And solving this problem usually means that you have to create some new idea, something that did not exist before. And I should also say that each of these steps take a certain amount of time. For example, to read articles and books about the topic, it can take maybe several weeks, it can take maybe several months, it can maybe take even several years. It depends on the topic, on the subject. And solving a problem sometimes, in my experience, sometimes it takes only a few weeks, sometimes a few months, sometimes many years. So the latest article I wrote, I solved a problem that I started to think about like maybe 14 years ago. So it took 14 years. It doesn't mean that I was working on this all the time for 14 years. It means I was working sometime when there were some new ideas I tried to solve. I couldn't, then I just put it aside. I came back sometime later, but after 14 years I could solve the problem finally. So it can take a very, very long time, or it can take just a few weeks. And then when you solve a problem, sometimes you just use ideas, techniques that exist before. Some other people develop, but you use it in a clever way to solve a new problem. But sometimes also you build a new theory to solve a problem. And this new theory can be applied to solving some other problems in the future. So this kind of work, when you have really very original new ideas, in a way more important because it can connect the problem to something completely, maybe even far away, and can build a bridge between two different fields of mathematics or even outside mathematics. So this is how it works usually, that you try to do research. And then after you have done the research, you have solved the problem, and then you have to publish your results. And in practice, this means that you need to go through all the steps of your solution, your proof. You have to check everything very carefully 3, 4, 5, 6 times. And this can take usually a few weeks, or it can take a few months, depending on the type of proof. So in fact, this part, in a way, for me, is usually the most difficult part, because I have to check every word that I have written in maybe an article of 50 pages, every word is correct, there is nothing wrong. And this really takes a lot of time. It takes a lot of energy to do this. And after this, you write the result as an article. You write an article. In mathematics, article is more standard, but in other parts of other departments, for example, in social science, they usually write books instead of articles. But in science, it's more tradition is that you write an article where you write all your proof and new ideas. This also can take several weeks to finish. And after you have written the article, everything is fine, you put it on the internet. The internet, of course, doesn't mean just put it on some random website that no one can see it. For mathematics and physics and computer science, there is a website that is called Archive. So almost everyone who writes an article, new thing, you put on this website. So every other mathematician can see that you have done something new. And if your article is very interesting, then a lot of people already start to read your article and try to use your ideas in their own work. So this is really important. It also shows having a network is really very, very important. For example, these Kurdish academies in different parts of the world can do very interesting things, and maybe they will never know about each other. But when you have a network, there is some place, I don't know, like Facebook, that someone does something and then all the friends, everyone know about it. This archive is similar, that when someone does a new work, everyone else would essentially know very quick. And then after you put the article on this archive, other people read it and maybe they give you a comment. They find mistakes in your work, or they just tell you this is related to something else, or give you references. Usually you wait for several weeks or maybe several months before you submit the article to a journal. And this is in a way, maybe the most important part. You have to publish the article in some journal, otherwise it just doesn't count. You submit the article to a journal, the journal sends the article to someone to read. And these are usually called referees. Maybe one, maybe two, and in extreme cases, maybe more. And these referees read the article very carefully. If there is any mistake, they will tell you that they found this mistake. Or even if there are some typographical things, they can tell you some trivial things. They try to improve the article for you. And in fact, all these things, by the way, this journal referee and so on, they are done for free. So this may be shocking to many people in other fields. In mathematics, all these things are done completely for free. When you submit an article to a journal, you don't pay to the journal, and the journal doesn't pay you anything. When you referee a paper, it can take even weeks. You don't get anything. You will not be paid anything. So usually the only way that you get paid is the salary given to you by the university. The university gives you a salary, and then you should do all this work based on your salary. So you don't get rich by doing this thing. And so the referee sends you a report, and then you revise the article based on this referee report and send it back to the journal, and finally they publish your article. And then the university will look at the article that you have published in journal to see how you are doing. So the more quality paper article that you publish, the better your situation will be. You can be promoted to something higher and higher. And so that's what I explained is the core activities, the research activities of a mathematician or an academy. But there are other activities related to research that we have to do. One of these things is attend seminars and conferences, like this seminar. This one is very general, but you have to attend seminars related to your field, related to your speciality. And that usually can be in your own university, somewhere nearby, or it can be in a very far away country, like in Japan or China. So, for example, I used to travel like 6-7 times a year to go to different countries to attend different seminars and conferences and so on. So this is an important part of an academic life. And again, it is similar to this CAR, this network, because this is a way of communicating with other academies. If you just sit at home all the time, you will lose your motivation after some time. But when you meet other people and discuss things, it can be motivating. It can give you ideas how to solve other problems and so on. And another thing that you usually do is to give seminars. You will be invited by other people to talk about your own work, your latest research, or you can organize seminars. You invite other people, you organize conferences, workshops, and this also can take a lot of time. And as before, you don't get paid anything. You will do all these things for free, essentially. And some other things you have to do is like advising PhD students and master students. That means that there are students, they want to do research, they want to learn how to do research, and you have to give them advice. You have to find a project for them, a problem to solve, and help them with solving the problem, and then finally write a thesis, and so on. This also can take time, and again, directly, you don't get paid for this kind of thing. It's just part of your responsibilities. And another thing you have to do is that you also need to refer other people's work. The journal sends you other people's work, you have to read it. So just in the last 1 month, maybe I already received 7-8 requests from different journals to refer papers. Of course, I cannot do all these things, but sometimes I just tell them, I give them a quick opinion about the paper, and I also suggest maybe some other people can refer the work, the paper, the article, and read it carefully. So that was basically the research part of our duty, and then the second most important thing we do is teaching. Teaching usually means you have to prepare and give lectures, and depending on the type of the lecture, it can maybe take just a little bit of time, but sometimes it can take really a very huge amount of time, especially when you teach something completely new. And you have to write the whole lecture from scratch, and that takes really a lot of time. And then you have to write examinations, and mark the examination. Again, you are all familiar with this thing. It takes a lot of time. And you also need to advise projects, not for like PhD students, but for undergraduate students. Sometimes you give them advice on how to write a project. Again, these things take time. And after teaching, there is also administrative duties. So there are things that are not research, not teaching, but still you have to do. And one of these things is to serve on different committees. So every university department has a lot of different committees about research, about how to write new courses, about how to admissions of new students, about how to run the department, the universities. And these are usually done by people, again, essentially for free. You have to just participate in some of these committees. And one of these things is about examinations. You have to manage the examination process. You don't really have to do that every year, but for example, this year I have to do, I am the chair of examination for undergraduate. That means that I have to spend a huge amount of time writing exams, reading other people who wrote the exam, and then marking the exams. And these things can be also very stressful and take a lot of time. So that gives you a summary of what mathematicians do. We don't just sit in our office and count from 1 to 2 million. We have a lot of different responsibilities, and all these things really take a lot of time. And one of the things that makes a mathematician's life in some sense very interesting, but also really miserable, is the flexibility of our work. Because we sometimes we can work, or we have to work even when we go on holiday. Sometimes we cannot sleep because we have to finish something by 2-3 days, by tomorrow. And this flexibility means that you don't have to be in an office to do something. You don't have to be in a lab with a lot of equipment. You can do just with a pen and paper or with a laptop, and that means that you are asked to do a lot of things because they know you can do it even if you go on holiday. So that's why flexibility is nice sometimes, because if you are ill then you can just stay at home maybe if you don't give lectures. But at the end of the day you will be punished somehow for that later. Okay, now let me go into mathematics, and as I said, I cannot really tell you so much about mathematics because it just needs a lot of background, but I try to explain some very, very simple things. In a way, this is not really mathematics in 21st century. It's like what? Baby version of mathematics in the last few centuries, not just this century. So what we do doesn't look like this at all. It's much, much more complicated, much more difficult. It's just, I cannot explain. Okay, let's start with some very simple things. My field, which is algebraic geometry, is mostly built around polynomial equations. Polynomials appear in mathematics and in many different fields of knowledge because in a way they look very simple. And so they are very natural, they appear very naturally. But in fact, studying them is one of the hardest parts of mathematics, because this gives you essentially algebraic geometry and also number theory. If we just start with algebra, just playing with equations, for example, you consider this equation x minus 2 equal to 0, and then you try to solve this equation. I'm sure all of you know immediately that there is one solution to this equation, and that's just taking x to be equal to 2. As simple as that. And then you can consider something more general. Instead of taking 2, you can take x plus a, where the a can be any number. So you try to solve something general, not one specific equation. And again, in this case, the solution is just x equal to minus a, so it's very simple. This is a general solution. It's a formula for solving this type of equation, no matter what a is. A is 2 or minus 2 or 5, doesn't really matter. Now, so that's degree 1 equation. If you go to degree 2 equations, then things become a little bit harder. For example, if we consider x squared minus 9 equal to 0, then again, all of you know that the solutions are 3 and minus 3. So that's not difficult. And if you consider x squared plus 4 equal to 0, then everyone knows from school that this equation does not have any solution, because x squared always gives you something positive or non-negative, and 4 is already positive. So if you look for solutions inside real numbers, you cannot find anything. So there is no real solutions, but still there are some solutions that are called complex solutions. The complex numbers were invented to solve this kind of equations that don't have any real solutions. And in this case, then the solutions would be square root of minus 4 and minus square root of minus 4. Because many people in school don't believe in such things, because they say there is no such thing as a complex number. In fact, they were called imaginary numbers. That means that they were not real. But they are actually very real. Now, more generally, if you have an equation of degree 2 where you take x squared plus bx plus a equal to 0, now b and a can be any number. You don't care. They can be any real number, and then you can find the solutions of this equation just by some simple formulas. So just one of them is minus b plus square root of b squared minus 4a, and then divided by 2, and the other solution is something similar. So the important thing is that in this case, the solutions can be calculated directly from these two coefficients, b and a. It gives you a general formula for solving degree 2 equations. This is already mathematics from 2,000–3,000 years ago. This is nothing new, even much older actually. And then you can consider higher degree polynomials equations. And the higher the degree, the more complicated things can become. If you have a higher degree polynomial of that form, then one of the things that we know about this equation is that it has at most n complex solutions. In fact, every equation of this form has solutions, complex solutions. Maybe no real solutions, but they have complex solutions. And one important fact is that you don't have more than n. You have at most n solutions. It cannot be more than the degree of the polynomial. But then you can ask, can you write down the solutions of this equation using only radicals? And by that I mean something like this, where you have, for the degree 2 formulas, degree 2 equations, you have formulas given by just some radicals plus, minus, and so on. So that you have some very simple operations just by taking roots. That's what radicals mean. Now, if you have a general degree n formula, can you write down the solutions of the radicals, just using radicals? The answer is not simple at all. In fact, for example, if you take the equation x to the 3 minus 5 equal to 0, then one solution is just the third root of 5. And there are two radicals and nothing more. Now, the answer to the question, can we write solutions as radicals, is yes, if n is less than or equal to 4. But in general, you cannot write down these solutions as radicals if n is more than or equal to 5. And this topic is called Galois theory. And in fact, it is a whole course, undergraduate course. It takes maybe like 20 lectures to prove this statement, to show that you cannot solve any general polynomial equation just using radicals. So it involves, in fact, one of the most interesting pieces of mathematics, which was developed like almost 200 years ago. So this is not 21st century mathematics, this is 19th century mathematics, but still we teach this in undergraduate, and it's really very interesting. Now, you can use only equations like I have discussed in the Galois theory, using fields and equations without geometry at all. But when you also mix equations with geometry, then you have algebraic geometry. You have two sides of a story, something geometric that you can see, just like pictures, and something algebraic, just equations. And how you mix these two is important. So for example, consider now this equation, y plus x equal to 0. Now you notice that I have two variables, two unknowns, x and y. Before I had only one, now I have two. And you can also increase the number of variables, but then things become more complicated. But for this equation, y plus x equal to 0, you can associate something geometric, some picture. And in this case, the picture looks like this. If you look at the solutions over the real numbers, the picture is like on the left side, this orange, red-orange line is the set of solutions, the points given by this equation. But if you look at the solutions over the complex numbers, the solutions will be a lot more, and they just look like a plane, look like a piece of paper. And this is the complex over the complex numbers. And the thing is that the shape of an equation can tell you something about the equation itself. Now, let's consider the shape of another equation now of degree 2. Y squared plus x squared minus 1. If you remember high school mathematics, this is the equation of a circle. So over the real numbers, the solution is just a circle. But over the complex numbers, the solutions look like a sphere, not a circle, just because there are a lot more points. But in this talk, I have to be very vague, so some of the statements are not 100% correct, but an approximation of correctness, because over the complex numbers, you have to remove some points to get a right picture. And then let's go to degree 3. The equation y squared minus x to the 3 plus x equal to 0, and then you can look at the shape of this equation. Over the real number, the shape looks like this. You have something look like a circle, and then you have like something else look like a half circle. But over the complex numbers, you get something similar to a donut. Again, you have to remove some points to get the right picture here. So a donut has some mathematical equation. It's not just, you can understand it mathematically, but I will come back to this equation later because it's much more important than it looks. It's much more than just a donut. And now if you increase the degree, then the shape becomes more complicated. It's just harder to understand. For example, it can look like something like this. It's just a random picture.
It's like a French patisserie.
Yes, now you get a donut with more hole on it, but you cannot find these donuts in the shop. So it can be just really very complicated, although on the topological, over the complex number, the shape can be actually simple. It's not so complicated up to some extra conditions. So the idea is to use geometry and also equations and mix these two things, and then you get algebraic geometry. And this idea probably is not new, it's already several hundred years old, but how we use it today is quite different. And this topic is also related to number theory or arithmetic geometry. The set of integers Z is just the set of usual integer numbers, which some of them are negative, -2, -1, 0, 1, 2, and so on. So everyone knows it. And then the set of rational numbers are just fractions of integers, a over b, where b should not be equal to 0, like 3 over 5 or 10 over 11 or whatever. These are rational numbers. Everyone uses these things every day, so there is nothing strange. Now, arithmetic geometry studies solutions of polynomial equations over the rational numbers, or something related to rational numbers. Before I discussed solutions over real numbers and complex numbers, but if you just insist on solutions in rational numbers, then you have number theory. Now let's go back to the equation x plus y equal to 0. This you can check very quickly that in fact it has many different solutions in Q. For example, just take x to be 2, y to be -2. That already gives you a solution. Or in general, you can take any rational number a, put x to be a, y to be -a, and then you have a solution. So you have infinitely many solutions, a lot of them. And in a way, this is related to the fact that this equation has degree 1. But if you go to an equation of degree 2, for example, x squared plus y squared equal to 0, then this has only one solution. Just 0 and 0, there is no more solutions in the rational numbers. If you go to the complex numbers, of course, there will be infinitely many solutions. But the point is just considering the rational numbers. Now, if you change the equation just a little bit, look at x squared plus y squared plus 1 equal to 0, then this has no solution over the rational numbers. That's because x squared and y squared, they always give you something non-negative, so you cannot find any solution. But if you consider x squared plus y squared minus 1, this is the equation of the circle, you again have a lot of different solutions, infinitely many. For example, you have x equal to 3 over 5, and y equal to 4 over find. So this is one explicit example, but you can generate a lot of examples just by taking some rational number t and letting x to be 1 minus t squared over 1 plus t squared and y to be 2t over 1 plus t squared. So this is important because it tells you a systematic way of generating solutions, and this is related to some interesting geometric facts. Now, in general, equations of degree 2 can have finitely many or infinitely many solutions. It just depends on the equation. But let's go to 1 degree more. Y squared minus x squared plus x to the 3 plus x equal to 0. This has some solutions in the rational numbers. For example, x equal to 0 and y equal to 0. This is one solution. Or if you take x to be equal to 1 and y equal to 0. Again, equations of degree 3 can have finitely many or infinitely many solutions, but it is much harder to decide whether an equation has solution or not. Even in explicit examples, it's quite difficult to decide. Now, if you consider all the solutions of this equation and make this equation the solution like a, b, and consider them as points inside a plane, like draw the picture of this thing over the rational numbers, then the set of these points has a structure of an algebraic group. If you know what is a group, it's interesting. If not, it's really hard to say what this means. Now, this group structure over some other kind of fields, finite fields, is used in cryptography. So at least maybe I can tell you this. When you go to the shop or you go to the ATM and use this card to get money, this uses this kind of equation. The secret codes for this kind of things, cards, so that other people cannot steal your money, are based on this kind of mathematical structure. So they have direct applications to everyday life. So this is just one example. Well, it's not only for ATM. For example, when you go on the internet, you buy something online, people cannot steal your information. It's because the codes are constructed using, for example, this is one type of a method that they use this kind of degree 3 equation to construct the codes. Now let's go to one higher degree, to degree 4. For example, with the equation f y to the 3 plus y x 3 plus x equal to 0. Now this has some solution in Q. For example, x equal to 0 and y equal to 0. But now the interesting thing is that this has only finitely many solutions. And in general, to decide, to prove that an equation like this has only finitely many solutions, in fact, is very, very complicated. There is a very deep result which says that an equation of degree more than or equal to 4 has only finitely many solutions if the shape of the equation is smooth. Now, smooth, I will show you a picture for telling you what it means, but just to prove this statement takes hundreds of pages. And the person who proved this thing was awarded a Fields Medal. And Fields Medal in mathematics is like Nobel Prize. So this is not something you can do just 2-3 days at home. It took 60-70 years until someone could prove this result. So, but the interesting is that even someone with high school mathematics background can understand at least what this is saying. That you have a simple equation written down like this. It's really very difficult to show that it has only finitely many solutions. Now, mathematically being smooth essentially means that your equation, you calculate the partial derivatives, if you know what that means, of the equation with respect to x and y, and you put in any solution, then one of them should now be equal to 0. And that mathematically, that means being smooth. Now, in the example that I showed you, you can calculate these partial derivatives, and they just look like this: 3ba squared plus 1, and the other one is 3b squared plus a3. If you show one of them is always not equal to 0, then it means that the equation gives you something smooth. Again, this is not 100% correct because I don't take into account points at infinity, but let's forget about it. But you can also find very simple degree 4 equation like this one, y squared minus x to the 4, and this has infinitely many solutions. And the reason is that because its shape is not smooth. And I can show you the shape of this. Over the real numbers, the shape of this equation looks like this. And if you look at the point at the origin, you have the shape somehow intersect itself. And that's the meaning of not being smooth. If you look at the other points on this orange shape, they are smooth because they somehow there is nothing breaking down at that point. But the origin, you have two parts of this thing and they intersect, and that means it is not smooth. And when the equation is not smooth, then you can have infinitely many solutions. So that statement then will fail. And now let me come to algebraic geometry. How much time do you have?
Yeah, we still have 15 minutes.
Okay, I will go a bit more than I will stop. Okay, maybe I already told you enough.
Actually, it was including questions.
Okay, I will
So if you can
go
finish.
quick and then maybe 5 minutes, then I will stop.
Yeah.
Now, algebraic geometry means that you systematically study polynomial equations in a very general sense. That means you take a system of polynomial equations in many maybe variables, not just x and y, x, y, z, and you can have any finite number of variables. So you see that even studying one equation is difficult, but if you have a system of equations, 100 equations in 50 variables, then it becomes almost impossible to directly say anything about the equation. So that's why then the geometry is more important here, because you essentially look at the shape of the solution, not just try to play with the polynomials themselves. But still you can look at the solutions of x. Now, assuming that these are defined over the rational numbers, you can look at the solutions again in Q. And you also look at the solutions in the complex numbers, so you have different ways of looking at this object. And this system of equations defines something that we call an algebraic variety, and I show it by just a letter x. And then the set of solutions in Q is shown by xq. Now, you can define the curvature of the shape of this geometric object. The curvature, at least, can give you something intuitive, though this is not exactly what I mean. For example, the sphere has positive curvature. It just means it looks like this, intuitively. And if you have just a cylinder, then the curvature is 0 because it somehow you have a constant shape, it doesn't change. And on the right side you have negative curvature because in some direction you have like this, but some other direction you have something like this, the opposite. There is bends in opposite directions, so it means that the curvature is negative. Now the curvature can be described using differential forms. Of course, I cannot say what is differential forms. But the general idea is that if you define curvature in the right way, in a more correct way, then if your shape has positive curvature, then it means that you expect to have many solutions over the rational numbers. And if you have 0 curvature, you again expect, in general, to have many rational solutions. But if you have negative curvature, then you expect to have few, maybe just finitely many solutions over Q. So, for example, if x is defined by y minus x equals to 0, then we say this has positive curvature because it looks like a sphere. But the degree 3 equation, in some sense, this has a zero curvature, and so again, in this case, you can have finitely many or just finitely or infinitely many kinds of solutions. But in general, you expect it to be large. And then when you increase the degree, then the curvature in this case becomes negative, so that's why you have a small number of solutions. And of course, these things that I formulate here, they are very vague, but there are many problems formulated in this field, and in fact, if you solve some of them, you will immediately get $1 million, for example. So they are not as simple as they look. Now, in general, the curvature of X is not uniform. At some places it's positive, somewhere it's negative, and so on. And then the idea, of course, one important idea is to try to transform X so that you have a uniform curvature in some direction. And this is another picture for curvature that I forgot to show. And then in this case, sometimes you have a fibration where, so in the direction of the fibers, the curvature is trivial, for example, and that helps you to study the set of rational points, for example. And yeah, so I will stop here. As I said, this is really just some very elementary aspects of what we do. What we do is much more than this. But I will stop here.
Thank you so much. So I think we have time maybe for 2 questions if you have any. No? I don't know if you have anyone here. Don't think so.
Or maybe
Yeah.
the Gödel's incomplete theorem.
Sorry.
The Gödel's incomplete theorem in logic.
Oh, okay. That's.
I remember studying that when I did computer science. Can you just? I still can't get my head around that in terms of like how. So can you explain that maybe in your words?
Yeah, of course, it's in a way not related to these things, but
it's
yeah,
logic and maths.
It essentially says that there are things that are true statements.
Yeah.
But using your theory, you cannot prove these statements. You know they are true because if you go outside your theory, you look from some other angle, you know they are true, these statements. But if inside your field, inside your theory, you have a certain number of axioms, certain number of statements you have already accepted that they are true, you can never derive these other statements from the one that you have already accepted. That's what incompleteness means. It means that there are things that are true, but you can never prove them.
And that's been proven.
Yeah, of course. That's
I still can't get my head around that because in
it's
order to
not
prove
easy.
that, you need to.
It's not easy to prove that itself.
Okay, no worries. Thank you.
Yeah, I have. First of all, I got embarrassed because you said this cubic and quadratic equations are for 2,000 years ago because I'm still using them in my research. So I got embarrassed because I used this basic things. My question is related to technology and mathematics, because nowadays I see many, research in many domains are driven by technology. So technology influenced research in many areas, including mine, which is logistics and supply chain. So now, what's the interaction between mathematics and technology? So is it mathematics driven by technology, or is it in inverse?
Well, there is a two directions. So in usually every mathematics department has 2 parts. One is pure mathematics, one is applied mathematics. And this applied part is directly connected with technology or with physics or chemistry or biology, with other parts of science. And so they communicate with technology and so on, and they can get equations, they can get problems that are motivated by technology, and then they try to solve these things. But pure mathematics is a little bit on the left in the sense that sometimes we get questions, and maybe not directly from technology, but from applied mathematics. And then we try to solve those things. But there are also a lot of things that are not driven by technology at all. It's just the internal evolution of mathematics. But what happens is that a lot of ideas, for example, this degree 3 equation that I mentioned, people studied this thing like, I don't know, more than 100 years ago, and then after 100 years, people realized that you can use these equations to define codes to make the internet secure. So that's what also usually happens. We do something now, maybe 100 years later someone will use these things. So yeah, there are two ways.
Thank you. Do you have any other question? I think we don't have any question from these guys here.
Is there anyone?
I don't know. Anyway, thank you so much. It was a pleasure to have you here, Kۆچەر. Thank you so much.